Good afternoon all of you. So today we discuss about the memory management function. So in this we are going to discuss basic memory management, swapping, virtual memory. In paging we are discussing 4 more concepts: paging replacement algorithms, modeling page replacement algorithm, design issues for paging systems, then implement issues for paging, then discuss segmentation. So these are the contents we are going to learn about memory management function. Now what is memory? Then we are going further about the management. Now what is memory? Memory is a linear array of byte that holds the operating system and program. That means program and operating system is going to be stored in a memory, and memory is a collection of bytes. Okay, each cell is named by a unique memory addresses. Okay, so each memory cell is hold a unique memory address. Processes are defined by an address space consisting of data, text and stack regions. Okay, so processes may contain data, text and stack, and that all information is going to be stored in a memory, and memory having a set of bytes. So program execution, CPU fetches instruction from the text region according to the value of the program counter. Each instruction may request additional operands from the stack regions. Okay. So memory management, programmers want memory that is large, fast and non-volatile. Okay, that is the requirement of the program. Programmer always need large memory so that it runs or execute the large number of programs on large number of process. So programmers require large memory, fast memory for fast execution, non-volatile memory. So in memory we have a number of different type of memories according to their performance. For fast memory or expensive memory we have a cache memory. Okay. So if we think about the medium and medium price memory, that is the main memory, and slow and cheap price memory is a secondary storage memory. Okay. So there is a memory hierarchy system. So these memories handled by a memory hierarchy. So now in multiprogramming we have a different type of memory, and we just partition the memory depends upon the execution of the process. Either we dynamically partition the memory or dynamically allot the memory, or we also partition the memory with fixed partition. Okay. So like this we have partition a memory with a fix. Operating system take 100 kilobyte, then partition 1 200 also take 100 byte, then 200 kilobyte memory is to partition 2, then 3, and according to their processes we going to partition the memory. And if any process having a memory space about 100 kilobyte, then that process is come into partition 1. Okay. If a process come that wants to take memory according to their process, it's want to take 3 kilobyte memory, then that process come in a partition 3. Okay. So this is a fixed partition in multiprogramming. So this is a multiprogramming modeling. According to the CPU utilization, we can observe the multiprogramming speed and multiprogramming efficiency. Okay. So naming and binding, how we are relocate the address in main memory. Firstly, we convert the symbolic names into logical name, then that logical name converted into physical name. Symbolic name like name of a student, logical name like a student class roll number. Then if you want to trace that particular student in a board, then that class roll number is converted into a registration roll number. Registration roll number is a physical address, logical name is a class roll number, and symbolic name is the name of the student. So in this way we are converting a logical into physical. So in a operating system language, we are saying that symbolic name is a name of the variable, logical name, logical address is generated by the CPU. Then we are adding some bits into the logical address that converts that logical address into a physical name. Okay. So symbolic name is a path of a file, program name, printer name, user name, and logical name used to label a specific entity. Either it will be a process ID, job number, device number, user ID, whereas physical name is the address of entity, address of any process on disk or memory. Now what is binding and how many different type of bindings? We have 3 type of address binding. First is compile time, second is load time binding, third is execution time binding. Now what is binding? Binding is the linking of file to the memory. Okay. So address binding, fixing a physical address to the logical address of the process address space. Now compile time binding means when we are compiling a program, then that program link their values to the memory. If program location is fixed and known ahead of time, that means before execution we know the exact position of the program in the memory. We exactly know the position and know how much byte it going to occupy in a memory. Okay. So second is load time binary. That means if any delay comes till the load time, that is load time binding. If program location in memory is unknown until runtime and location is fixed, that is load time binding. Execution time binding, if process can be moved in memory during execution. Okay, so that means binding till delay till the execution of execution time. Okay, so that is execution time binding. That means linking happened in runtime while the execution or program is going to execute. Okay. So there is 3 type of binding. First compile, load and execution. Here is an example. So in compile time address binding and load time address binding, notice this, these 2 addresses is same, but the address in the execution time is different. Okay, because we are adding a base address into the logical address. Here is 100, we just add the base address 1000, then 100 plus 1000 is equals to 1100. This is the physical address. Okay, at the compile time. So in this way we are adding the base register value, and compile time address binding and load time address binding is the same. Addresses are same, but address are different at the execution time. So dynamic relocation with the base registers. So these dynamic location can be managed by the memory management unit. Dynamically converts logical address into physical address. Memory management unit contains base address register for running processes. So program generates addresses, then adding the base register address that is managed by the memory management unit, then it converted into physical memory address. That means that particular address is placed in physical address in memory. Okay. Protection using base and limit registers. Main memory protection. Base register gives starting address for processes. Okay. So while we are converting a logical address into physical address, then CPU generates a logical address, then add some base address register values, then we have add some limit register value. Here is the condition: if the limit value is increased, that means it is greater than, there is some error. If it is less than, then add some base register value, then it converted into physical addresses in the memory. So what is logical and physical address? We are talking about this logical address is converted into physical. Now what is logical and physical address? The concept of a logical address space that is bound to a separate physical address space is central to proper memory management. We also say that logical address is a virtual address that is generated by the CPU, whereas physical address, that address is seen in a memory, and that physical address is generated by the main memory. So logical and physical addresses are same in compile time and load time, okay, but logical and physical address is different in execution time. Execution time, logical and physical address is quite different. So there is some features of memory management. First is relocation. Relocation, there is two type of relocation, static and dynamic. Relocation means while we are swapping in or swapping out the process into the memory, their relocation again is different. It can be a static and dynamic. Second is protection. Protection means how we are protect our memory either in read mode or write mode. Sharing. Third is sharing. Sharing means how many processes are going to be shared and where we are going to share the processes. Okay. Logical organization, how we organize a memory in logical memory. Physical organization, how this process is organized in a main memory. Okay. So last is memory compaction. So there is various method used by operating system. First is swapping, virtual method, paging and segmentation. So swapping means when we are swap the number of pages into the main memory. Okay, swapping means if we have 10 pages in a single memory and 11th page is request for spacing, then what we can do, we are just replacing a one page with previous value. Okay, one page with their recent request value or recent request page, that is swapping. And there is different way we are swapping a page. First is we have add only operating system and A page, then we have request for operating system, then A and B page. Okay, because we have a number of space, then there is no need for any swapping. Swapping is required when already all memory is full. Okay, so third, operating system A and B, third page is also having a space where operating system B and C. A is a most first coming page. Okay, so it is swapped, again swapped by D. D needs more space, that is not recently available, so A has to be replaced by D. Then operating system D and C, then operating system D, again we some process need a page A, so again it can be swapped with with any page. Okay, so memory allocation changes as processes come into memory and leave the memory, that is the swapping. So swapping can be increased or decreased. Okay, so in this way we have only two processes and one operating system. Okay, so these two pages may be grow more. Grow more means in processing maybe their value is adding. So if value is adding more, then their page require more space, so it may be grow with their actual position. So in this way, operating system, A program, A data, A stack, that means a single program need a more and more space during their execution. Allocation space for growing data segment, allocation space for growing stack and data segment. So memory management with bitmaps. So there is a 5 1 bit and 3 0 bits. That means 1 bit represent there is some data and memory is occupied. Where 0 0 0, that means there is a hole. Hole means there is a free space and can be utilized. Totally we have 8 byte address of A. From that we have only 5 bit is going to be used. Okay. So in this we have 5 processes, and these 5 processes take their memory starting address of the memory and the particular length of a particular page. Like H represents a hole means there is a space, free space, where 0 is a start address and 5 is the total length of the process. So P represents process. Okay. So part of memory with 5 process and 3 holes. Memory management with linked list. That means a memory can be managed with the linked list having the 3 nodes. One is address of previous, another is the data, and third is address of next instruction. So managing memory with linked list. We can manage the memory management with linked list in different ways. First is first fit. That means we are searching a free space or first we are searching the free holes. Then we are placing a page in a memory. Next is next fit. Start from current location in the list. Third is best fit. Best fit means we are finding a smallest hole in a memory. Smallest hole means we are finding a smallest free space in a memory. Worst fit means we are finding a large hole, large space available in a memory. And quick fit keeps separate list for common sizes. Now what is virtual memory? Virtual memory is required when we have a limited memory, and virtual memory illusion the user that they have a large number of memory to execute a large program but with a limited memory. That means we have a limited memory but we show the user that we have a large number of memory in our system. So virtual memory, separation of user logical memory from physical memory. Only part of the program needs to be in memory for execution. Logical address space can be much larger than physical address space. Need to allow page to be swapped in and swapped out. Virtual memory can be implemented via paging and segmentation. Now virtual memory, virtual addresses are generated by the CPU, that is managed by the memory management unit, and memory management unit sends a physical address to the memory to relocate the particular address. Now what is a paging? The relation between virtual addresses and physical memory addresses given by page table. Okay. So page table is a collection of number of pages or frames. In this way, page table having a number of bytes. These 4 bits shows the page in a page table. Okay. And rest of the bit shows the virtual or logical address. That logical address directly come into the physical address. But this page address find out the base register value. This is the 0012 binary value is 2. Now point to the 2 having a base address 110. That 110 is the base register value, that this base register value is added into this offset 12-bit address directly to the input. This is the whole about physical address conversion. Okay, so this is the logical or virtual address converted into physical address. So in this way, a page table is working into number of parts: offset, PT2, PT1, page table 1 and page table 2. So, page table can be modified and should be enter reference number, caching disable and present and absent bits. If there is any protection bit, add some protection bit, and then page frame numbers. Okay. So, if any page is going to be modified, then their bit is also highlighted. That means if there is a 0 bit, that means there is no modification. Later on, if you want to add some content on it and modify the table, then modify bit is going to be 1. Okay. Or present or absent means, is there any page, is this page is present in a memory or not? If that page is not available in a memory, then here is absent. So, if that particular page is present in a page table, then show present. Okay. So, this is a translation Lookaside buffer. This table shows the overall table contents. Valid virtual page, how much virtual page is exist in a table, modified, which page is modified or which not, and protection mode, which page is going to read and write mode and which page is only in read mode. Okay. So, this is page frames. Inverted page tables. Inverted page table and traditional page table. This is traditional page tables and this is inverted page tables. Inverted page tables have different entity and previous traditional page have different entities. So, there is some methods and algorithms in which we are replacing the pages. So, this is page replacement algorithm. So, page fault force choices, which page should be removed, which page is going to come and which page is going to out of the main memory, this can be decided by some sort of methods and algorithms. Not directly we can or randomly we can't pick any page and replace that particular page. There is a proper method to replacing a page. Modified page must first be saved. Better not to choose any unused page. Okay. So, there is number of algorithm. First is optimal page replacement, not recently used page replacement algorithm. FIFO, that is first in first out page replacement algorithm. Second chance algorithm, clock page replacement algorithm, least recently used. So, what is first optimal page replacement algorithm? Replace page needed at the farthest point in future. That means if a particular page is entered in a main memory and that page going to be used in a future, not now, so that page can be replaced. Okay. Not recently used page replacement algorithm, that means that particular system is not recently used but used in later on, but not recently. So, that page can be replaced. And pages are classified as not referenced, not modified, not referenced, modified, reference, not modified, reference and modified. So, not recently used page, remove pages at randomly from lowest numbered non-empty class. So, third is first in first out page replacement algorithm, that means a particular page come first, that go firstly. Okay, that means which pages come first and that particular page replaced first. Maintain a linked list of all pages in order they came into memory. Page at beginning of list replaced. The disadvantage of FIFO is paging in main memory, the longest may be used. That means the particular page come in first, so that may be possible that particular page must be required for a long purpose. Okay, so this is the disadvantage of FIFO. So enhanced version of first in first out is second chance page replacement algorithm. Page loaded first, most recently loaded page, then A is replaced with first one. A is treated like a newly loaded page because its modified bit is changed, so that's why it come into first position. Now next is clock page replacement algorithm. When a page fault occurred, the page the hand is pointing is to inspected. The action taken depends on the R bit. R is equals to 0, that means page can be replaced. If their value of R is 1, that means clear R and advance hand. Okay, so if the value of R is 0, that means a particular page is going to be replaced, and if R value is 1, that means reference bit is 1, that means it cannot be replaced. Recently used, least recently used algorithm. Assume page used recently will used again soon. Okay, throw out page that has been unused for longest time. Must keep a linked list of pages, most recently used at front, least at rear. Update this every memory reference. Alternatively, keep counter in each page table entry. Choose page with lowest value counter, periodically zero the counter. That means least recently used pages can be swapped. That means if their value can be used later on, then that value can be replaced or swapped with the request page. So this is overall summary of page replacement algorithm. Optimal algorithm, not implemented but useful as a benchmark. Not recently used algorithm is very crude. First in first out might throw out important pages. Second chance, big improvement over FIFO. Clock is a realistic. Last recently used algorithm is excellent but difficult to implement exactly. Not frequently used, fairly crude, approximately to least recently used algorithm. Now aging algorithm is efficient algorithm that approximates least recently used well. Working set algorithm somewhat expensive to implement. So WS clock is a good efficient algorithm. So there is number of replacement algorithm through which we can replace and swap a particular page in a main memory. So this is a modeling page replacement algorithm. So here is some problems related to FIFO, first in first out. Here is a FIFO with 3 page frames, FIFO with 4 page frames, and P's shows which page replaced, show page fault. Here is a stag algorithm, state of memory array, and M after each item in reference string is processed. Now what is the advantage of page size? First is less internal fragmentation. Second is better fit for various data structure and code section. Less unused program in memory, and disadvantages is many pages are needed when we are going to replace, and large page tables are required for manages the number of pages in a memory. We require a page table for taking a record of number of pages come in out in a main memory. So page size also there is an advantage. Overhead due to page table and internal fragmentation. Okay, so when we are look after and designing a page tables, it also may increase the overhead. It also require internal fragmentation. So overhead can be calculated as overhead average processing size in byte into page entry upon page size in byte plus page size in byte divided by 2. This is page table space, internal fragmentation, and optimize when p is equals to 2 se underscore. Okay, अंडर रूट लेंगे, then we calculate the